morning. Now we are going to start our second session. So today we are having the special guest, Professor Dr. Rupnarayan Roy sir. So may I now request coordinator of the program, Dr. Arvind Kumar Jain sir, to felicitate or welcome him with the power program of today.
Sir, welcome.
Thank you, sir. Thank you very much.
So, before going to start the second session, I would like to briefly introduce the speaker of this session. So, we have with us Dr. Rupnarayan Ray. Dr. Rupnarayan Ray has completed his B.Tech in Electrical Engineering from Kolkata University and Master degree from the BE College, West Bengal. He also obtained the Ph.D. in Electrical Engineering from Jadavpur University in the field of power quality mitigation. So, Dr. Ray is a senior most faculty. Dr. Ray is a senior most faculty of this department. He joined the department in the year 1987. At that time, it was known as the TEC, Tripura Engineering College. Later on, it is converted to the NIT Agartala in 2006. Up till he has published more than 20 papers in various journals and conferences. He is guided 3 Ph.D. scholars and 19 M.Tech scholars. His research interests are electrical machines and drive, power quality, harmonic mitigation, distributed generation. Dr. Ray is also associated with various professional bodies like Life Member of Indian Society for Technical Education, Fellow of the Institution of Engineers, Member of Indian Science Congress Association. So with this brief intro, now I would like to request Professor Ray to commence the second session. Sir.
Good morning, participants. It's a pleasure to interact with you and all the distinguished faculty members, scholars, and the participants. Very good morning to all of you. How many of you are faculty members? Just let me know.
Faculty member.
Faculty as
Mr. Madam and he is working in Polytechnic. He is also a student.
So before I start, let me say something in the lighter mood. My guru and my teacher used to say it is very difficult to teach a teacher. So I also believe in that. So I am not here to teach anything else, only to share some my experiences which I gathered during my journey. So here will be we will be discussing some issues related to DG or other distributed generations. So this is our major topic. Our focus of attention will be on that. Our quality is related to DG. Now, as the current topic is related to our microgrid and smart grid, so these are the very relevant issues, I think. Now, as soon as we talk about power qualities, so we like to highlight some of the issues like your swelling, so then the sag of the voltage, then the harmonics and all these issues. Now, before that, let us first start how this problem comes into the picture. Okay. So as you know, the distributed generations, this term itself came some couple of years ago. So before that, the conventional power supply was introduced long back, say 1881. The actual power scenario came into the picture, and then this is just the brief introduction I am talking about. Then centralized power system was being considered. Then subsequently the green power and all these things came into the picture. So this green power and green resources are now playing a pivotal role in this power system scenario. Okay. So then the deregulation of the system, it also came. Deregulation means now several power distribution companies are coming into the picture. So they are free to inject their generation or power into the grid, because we are to meet the demand, enormous demand of the power supply. So our private operators, they are coming into the picture, they are also feeding their power into the grid. So deregulation came into the picture, and along with that the green power or the DG came into the picture. Now these are the some of the different type of DG, distributed generations. So you are most probably aware of this. I am not going to discuss because this is not our main topic, just these are relevant. So reciprocating engine, micro turbines, then industrial combustion engines, these are some of the DG. Then fuel cells, and obviously most important one is the photovoltaic. And there are some other sources also, wind turbine and the other DG sources like your bioenergy, geothermal. These are of lesser important because very less quantity of power can be generated through this. It is not an enormous power can be generated. Now, as far as this green power or the distributed generations are concerned, most of this power which is generated is in the form of DC. That is your DC power. So the problem which is related to this, to DG, first one is your incorporation of power sources in inherently passive network gives voltage rise problem. Whenever you are injecting power, in many cases there is a voltage rise. So that has to be controlled. This is a very inherent problem. Whenever you are feeding power, then there is a voltage rise. And some private operators, as you know, they are charging their power as they are feeding into the grid. So I should not say this thing, but this is some of the commercial policies of the private operator or the private player. They used to feed their power in a massive way, and as a result there will be enormous voltage rise if there is no control, because whichever power they are feeding, they will be charging the power as per their feeding. Okay, so they will always try to feed maximum of their power. So that is the problem. Then inertia problem is there. Then almost every DG source is a source of harmonic pollution. How it is source of harmonic pollution? I told in the very beginning that most of the power, whether it is your photovoltaic or your even wind turbine, these are the most commonly used in India, or your fuel cell, most of these power are in the DC form. So our system is not in the DC form, it has to be inverted, right? So what is the common practice? We are using the converter circuit to convert this from DC to AC. So as you know, in a converter circuit we are using devices which can be turned on and turned off constantly, and as a result the harmonics will be generated in the inverter itself. It is a natural phenomenon. Whenever you are using the inverter from DC to AC, then harmonics will be injected. What is the reason? The reason is that it is not a pure AC, always there is a source of harmonics. So whenever you are injecting power, then you are injecting the harmonics into the system itself. So this cannot be allowed. You are polluting the whole system. So what they have done? They have set certain standard. And the most common one, okay, so I will be coming to this point later on. Now if it is a harmonics injected, that is the voltage harmonics, right? So it is already injected into the system. Next, whenever you are connecting the loads, non-linear loads, then again you are drawing the non-linear current. That means the problem will be multiplied. Even the load, if it is a linear load, due to voltage harmonics, then the current will be nonlinear. Now your source is nonlinear, then again you are connecting some nonlinear load, so it is a multiplier. So that is a very critical situation that has to be taken. Now incorporation of DG in power system may be done in two different situations. One is your grid connected mode, this other one is your microgrid mode. So microgrid mode, it is almost a standalone mode. If you have the local sources, then you can connect all these things, then you can form a microgrid and meet the local demand. Otherwise you can feed the power to grid also. So in the grid connected mode, due to small size of DG, they are disconnected from the grid in case of any disturbance in the lines. If there is any problem in the distribution lines or any sort of problem, then immediately it has to be disconnected and it is done exactly. But in the microgrid, the chances of problems are less. So these are some other issues, reliability and all these things, it has to be addressed. Now, as I told you, the major problem is your other problems like your swelling and sagging and other problems that can be mitigated. These are also serious problem, but most common problem is the injecting harmonics into the system. That is the inherent problem of your teaching. So how to mitigate it? So our objective is here to eliminate the lower order harmonics with lesser number of switching in the inverter. Second one is by using the soft technique, this PWM inverter as well as in multi-level inverter. Then to utilize this same technique in a grid connected DG, particularly in reference to harmonic elimination. So these are our objective. So our problem is to eliminate the harmonics. It is, before doing it, keep it in mind, it is not possible to eliminate any sort of harmonics completely. It is not possible. What is the harmonics is, you know, it is some multiplication of your frequency, and that is available in the along with fundamental one. Say your third harmonics, it is 3 times of your fundamental frequency, then fifth 5 times of your fundamental frequency. So up to which order of harmonics you will be considering? That is the problem. You cannot eliminate up to 100 harmonics. Not possible. Theoretically you can, but the problem is that for eliminating 100 number of harmonics, you require several times of your switching, which is not possible. So what we are doing, we are restricting the elimination of harmonics up to a certain level, a certain order, maybe up to 25th order, 30th order, 50th order. Now there are certain IEEE specifications up to which you can eliminate or you have to eliminate. Right. So this is our intention. Now the most common technique is your PWM technique, how it is eliminated. So what is that technique? You have this is just a review of your earlier knowledge. It is nothing new. These are all known to you because in power electronics classes it is being taught since long back. So how it is done? You have two. One is your reference signal, the other was your triangular carrier wave. This is the most common one. You can find the switching instant at these points, at this point, and you can go on switching. Right. Now this is your equation. Analytically how it can be done. This is your reference sine wave. Then the triangular carrier wave. This is the equations. Okay. Now this is the carrier wave voltage Vc and the omega c, the amplitude and angular frequency. Now the harmonics of output voltage in case of your bipolar switching, this can be expressed. This is your equations, an equal to 4 by n pi and all these things. So up to k equal to 1 to m you can consider. Now in case of this sine triangle switching, this is the most common phenomenon. If you go for eliminating with this technique, you will have a sideband. First dominant harmonics will be appearing, this one. First appear at a frequency of this one, MF plus minus 2 FR. What is this one? This is the MF is your frequency modulation, FC by FR. Right. So at that frequency plus minus 2, that is sideband, with a side bend you will have the first dominant harmonics. Up to that, all other harmonics will be eliminated if you go for this switching. Right? So in sine triangular PWM modulation, if you select a particular frequency of carrier wave and a reference wave, then up to that value all harmonics will be eliminated and the first will be appearing at a frequency of MA plus minus twice FR. This is a common phenomenon. This is well established phenomenon. So then multiple of that again it will be appearing. So this is the standard practice in PWM technique for harmonics elimination. But here the problem is that several number of switching is required. Number of switching is very high. So as you know, there are restrictions in number of switching. You cannot go for infinite number of switching. So theoretically you can eliminate up to 100 order of harmonics. This is not possible practically. Now how to compute the Ph.D? That is total harmonic distortion. This is the equation for total harmonic distortion. So where you can find, this is A1 is the fundamental one. This one is the fundamental A1, 1 by A1 square. So n equal to 5 to infinity n by n square, this one. N equal to 6i plus minus 1. So why we are considering from n equal to 5? Actually the question comes, why from 5? We are considering from 5th harmonics. While computing the percentage Ph.D, say up to 30th or up to 25th you want to compute. So we are considering from 5th, not before that. We are not considering 3rd. What is the reason? The reason is that the 3rd, 9th and this triplet, these are automatically eliminated in a balanced system, right? A balanced three-phase system. So we are dealing with a balanced three-phase system. So in that the triplet frequencies are eliminated. The even harmonics will not be here due to symmetry. Only odd harmonics will be present, that too not the triplet. So that's why we are considering from 5th and then 7th, then 9th will not be considered, then 11th. So in that way it is chosen. So in that way it is chosen n equal to 6i plus minus 1. Right? So this is the simulation, I mean from the experimental data, sine triangle modulation, how it is done. This is the pulse generated using this sine triangle modulation. So this is the common phenomenon, nothing new, up to this nothing new. This is the standard practice of eliminating harmonics. Now, as I told you in the beginning, the problem is the number of switching. You can eliminate up to nth order of harmonics, but the number of switching will not be such an enormous number that you cannot practically, I mean you can incorporate in your experiment. So that is the problem. Now this is the computational technique of SHE, that is called selected harmonics elimination, SHE. Now what is done in that way? You know, some of the harmonics, lower order harmonics, will have much more impact on the fundamental. Say for your 5th, 7th, 11th, 13th, this will have a huge impact in distorting the fundamental. If you consider the higher order harmonic, like your say 23rd, then your 25th. So these order of harmonics, these are far away from the fundamental and this will have lesser impact. I am not telling it will not have any impact, but it will have lesser impact. So fundamental will be more affected by the lower order harmonics. So what they try to do, they wanted to eliminate some of the harmonics which are very close to fundamental frequency, that the lower order harmonics. So this selected order harmonics elimination technique came into the picture. Now how it is done? The fundamental component is assigned the desired value. Fundamental value you cannot compromise with. It must have a desired value. Then the other harmonics has to be eliminated. So what is done? The other selected order harmonics in the equation itself, say your third, fifth or seventh or 11, in those equations you are equating to 0. That means it has to be eliminated, right? Then a set of non-linear transcendental equations are formed. A set of equations are formed and you are to solve these equations to find the exact instant of switching. So naturally this instant of switching will satisfy those equations. What are those equations? Your fundamental has an assigned value and the other harmonics which you want to eliminate is equated to 0. So these equations will be satisfied, right? So once you are solving these equations, you can find the exact instant where to go for switching, and then those equations, those harmonics will be eliminated. That selected harmonics will be eliminated, right? So this is the equation. This is the equation for function a n sin n L alpha and b n cos n A alpha for your bipolar switching. This is the nature of bipolar switching, this one. Now due to quarter wave symmetry, as I told you, the even harmonics are absent, that is this Bn is 0, this one is 0, only odd harmonics are present. The amplitude of nth harmonic An is expressed only with the first quadrant switching angle. You can express by the first quadrant, that is up to 90 degree the angle which is required. So this is alpha 1 through alpha m, and this is your condition. So 0 to pi by 2, that is 90 degree. This angle is the first quadrant angle. So you are to find those angle after solving this equation. Obviously that will be satisfied, right? So these are all known facts. I am just discussing the available technique which are being used so far. So this is your fundamental one. If you put A1, that is n equal to 1, then A5 is for your fifth order harmonics, then equate it to 0. Similarly, any order of harmonics which you want to eliminate, equate to 0, and the fundamental is assigned with a value m. So this value you cannot compromise, right? Now you have to solve this equation. Now what is the problem with that? That is the real problem. You cannot solve this equation very easily. It is very difficult. So m minus 1 number of harmonics can be eliminated with m number of switching angles. Obviously, the number of variable, if it is m, then m minus 1 number of harmonics can be eliminated because 1 is already assigned for your fundamental. So rest m minus 1 can be eliminated. So if you are going for 5 switching angles, say per quarter, then you can eliminate 4 harmonics. So 5 equations you can solve these 5 equations to get 5 variable. So for 5 number of switching you can eliminate 4 harmonics and 1 is for your fundamental. So for example 5th, 7th, 11th, 13th you can eliminate with 5 number of switching per quarter. Triple harmonics are eliminated in 3-phase balance and these are not considered. Now the problem is that these equations are non-linear. So that is the main problem. Analytically you can solve it, but these are non-linear, so it is very difficult to solve. It shows multiple solutions. So which one is to be taken? You have for 5 variable you have multiple solutions. So which value is the final one which will be giving you the optimal solution, you don't know. So that is one problem. You have to check it. Second problem is, in some places it shows non-linearity. No solution is available in certain points. So how to find the switching angle at those points? So that is another problem. So now this technique, SET technique, was being used. Now it has several other problems involved in terms of solution of this set of nonlinear equations. So now people are thinking of evolutionary computational technique. What is it? Some soft computing technique. So there are several soft computing technique available, like your GA, genetic algorithm, and N colony optimization, particle swarm optimization. So several techniques are used, available. Out of this, one technique, PSO, that is called the particle swarm optimization technique, which is found to be a very effective one, and that is applied here. So right from here, the new concept comes. Earlier, the PWM technique and the SHE technique were being used. This is nothing new. This is a commonly known fact. Now from here, the evolutionary technique came into the picture. So different from this, a new evolutionary technique, PSO. So it was actually developed by Everhart and Kennedy in 1995. So instead of using genetic operators, each particle adjusts its flying according to its own flying experience. What is it? So let me tell in brief. This is beyond the scope of this discussion to go through it in detail. Just I am telling you, this is a natural phenomenon. So say for your bird flocking or your fish schooling, what is happening in a bird flocking? A flock of birds moves here and there in search of food, right? Whenever food is available, the flock of bird actually emerges or converges at a particular point and come to that point for collection of food. So inspired by this natural phenomenon, they have developed this technique. This is a very effective one. So I am asking you one question. Have you ever seen in a flock of birds to collide with each other? Never. They are running, flying at a very fast, at a very high speed and in different directions, constantly turning and roaming here and there. But you will never find these two birds in collision. So in a complete, in a flock of birds, you will never find two birds to collide with each other. How they are maintaining it? So there are two variables. One is your velocity, the other one is the space between two birds. So they are maintaining these two. One is the distance, the other one is the velocity. So they are maintaining in such a way and they are adjusting in such a way to converge at a particular point where food is available, and then they are coming to that particular point. So that is the beauty of nature. Nobody taught them this technique and all this thing. By experience they have gathered all these things and they have found this one as an effective and they are converging at a particular point. So inspired by that, this is developed and this is the mathematical model of that one. So this is the ith particle, that is the in d-dimension space. This is represented x1, x2, x3, like that. Now here the velocity vector, that is also here vi, this is the velocity vector and this is the space vector x. And with these two, this is your mathematical formulation here. What is done? Every time they are changing their position and velocity and then finding the best position. That is called the p best position. This one is the p best for the present best, right? And they are comparing with the g best at that moment and finally arriving at a point which is called the g best, that is the global best position. Now as you know, in any linear solution, if you go for the local solution, you might be finding a particular solution at a point and it may appear as the best solution. But in real scenario, that may not be the best one. Say you have an oscillation, but the chalk is available or not? Marker is available. So magnitude is this one and you have a velocity like this. Now in our random, iterative method, what we are doing, every time we are comparing with the next velocity, right? Say here you are comparing with this one, so it is lower than it is coming to here this position. So at this point, if you come to this point, you will compare with the next velocity, next position. So the next position again it is increasing. So you will find it, this is the best solution in the normal method, iterative method. Whereas the best solution or the global solution or the global best is not here, it is here. But as you are comparing with the next velocity, next value, you are finding this one as the best solution. So in this iterative method, you cannot find the global best solution. Right? That is the limitation of the normal iterative method and all this thing. Now in the global search, you can find the G best. So G best here available at this point. This is your G best. So how to find? This is the random search method, and you can find it only by this technique. So here every time they are considering as a best position and then comparing with the next best position and finally arriving at the global best position. So this is the mathematical formulation. Every time the position is changed and that position is set with the new equation of the velocity. So this position and velocity is compared, then finally the global best position is found. But it is inspired by the nature, as I told you. So this solution is having certain limitations. What are those limitations? I will be discussing later on. So C1, C2, these are the constants called the constriction factors. This you have to randomize it because this is the random search method. So randomized factor, function is there, randomized, and this is also used to randomize these values. So these are the inertia factor which is selected. Now this PSO technique is used here for the solution of the equations. These equations can be solved using this PSO technique. How it is done? This is a powerful tool. As a principal limitation of this, with the application of conventional pulse width modulation SHE, selected harmonic elevation, is been analytical difficulty in solving the nonlinear equations. These equations contain trigonometric term and transcendental in nature, therefore exhibit multiple solutions. These are the limitations of the PWM SHE technique. Now this is the equations. Now how they have formulated it with an objective function. They have formulated this function as an objective function, say this function with respect to alpha 1, alpha 2, alpha. We are considering only the first quadrant switching angle because this is related to first quadrant switching angle. Now these are the sum of the constant. Alpha should not be more than 90 degree and it should be between 0 and 90 degree. Then A1, the fundamental should be M, they should be equated with M, and here A5 is fifth. Instead of setting it to 0, we are equating with a constant value, that is epsilon 1. This is less than or equal to this one. What is this? Similarly, A7 is less than or equal to A2. Now these are allowable limits of individual harmonics. Now this is the interesting phenomenon. We are not equating those harmonics to 0. We don't want to eliminate those selected harmonics completely. Rather, we are restricting it to a specific value. What are those values? E1, E2, E3. What are those values? It's not E actually. Epsilon 1, these are the errors. So as per individual harmonics, as per IEEE 519, what is this? IEEE 519 is a code. This is made for your DG. This is an international standard set by this IEEE. Whenever you are feeding power to a particular grid, at the point of common coupling, PCC, probably you have heard that term, PCC, point of common coupling. At that point, your individual harmonics should not exceed a specified value and the THD should not exceed a particular value. That is the term set by the IEEE. So that is dependent upon your system voltage, right? So for different system voltage, the specification is different. So if you are having a 69 kV system as per IEEE 519 or 59 kV system, the individual harmonics should not exceed 3%. That is the international standard. Individual harmonics should not exceed 3% and the total harmonics distortion THD should not be more than 5%. Right? So that is 500. Now here we are considering 66 kV system, because in Indian system we are not concerned with 69 kV. We are concerned with 66 kV or 130 kV. So we are limiting it to 66 kV. And there also they have set the THD standard. I mean THD limit. How to calculate it? 5% considering up to 30th harmonics. You have to consider up to 30, not up to 10th or 15th or 20th. Up to 30th harmonics you have to consider for computation of THD, and then it should not be more than 5%, and the individual harmonics should not be more than 3%. So that is the standard practice in IEEE 519. So that's why we have set this value to epsilon 1, epsilon 2 and like this. So you can set up to 5% or 0.05 like that. Okay. So this is the algorithm, how it is done using that PSO mathematical formulation. So randomize these angles. This is a random sort method. So you have to randomize first. Randomize it. Sorry. This one alpha 1 to alpha t with an initial guess corresponding to number of population. Then so what is done here? You have to consider a number of population. No. So, is it पानी पीने का नहीं? You have to consider a set of generations. So in every generation you have to consider a number of population, right? So with that number of population you go for randomizing, then again go to the next generation, with that number of population go for randomizing. In that way it is coming or converging. So that is the algorithm here. For a particular generation index, number of population index is set, then with that value you are computing this A1, A2, A5, AN, all these things, and find the objective function. Now then minimize this F alpha. F alpha is the objective function. You have to minimize it subject to condition that A5, A7, A13 that should not exceed 5% and THD should be less than 5%. So this condition is that alpha in between 0 to 90 degree and THD means percentage THD, that is the objective function, that has to be minimized. So whenever it is coming to less than 5%, then you are accepting that value. Subject to condition that the individual harmonics, you have already put that constant, it will not be more than 5%, 3%. Individual harmonics should not be more than 3%. So you have put that condition constant and alpha should be between 0 and 90 degree. So that way it is computed and finally you are coming whether this P best is exactly equal to your G best, that is global best. If it is exactly same, then accept this, then find this alpha 1, alpha 2, alpha 2. So in that way we have computed the percentage THD. Now interestingly, I will be showing the result in all these things. This is a bit computational, but I am trying to give you the idea how it is done and you should think of it. So first question comes to mind. In the earlier case, we are eliminating these harmonics completely, right? Say we are considering 5 switching angle. So maximum you can eliminate 4 harmonics. We are targeting 5th, 7th, 11th and 13th harmonics. So by the conventional technique, you solve these equations and you put these respective harmonics equating to 0, so that will be completely eliminated. Then you find the THD, compute the THD. This is one method. Same system, you go for this technique where you are restricting these individual harmonics 5th, 7th, 11th, 13th to 3%. You are limiting to 3%. You are not completely eliminating, you are limiting to 3%. And total harmonics, it should be less than 5%. You are minimizing the objective function to less than 5%. Now the question is, In the first case, you are eliminating those harmonics completely. In the second case, you are not eliminating completely. You are putting to less than 3% value. Might be 1%, 1.5%, 2%, 2.5%, or 3%. Now, with that value, how THD will be less? How the THD will be less? This is the question. So that is the most confusing one. Many people might have that confusion, but this is not at all confusing. I will be explaining this thing. Though it is not 0, but still the THD is less than the earlier one, which is computed, considering the selected harmonics to be 0. How it is done? See. So these are the switching pattern which are computed using this technique for bipolar switching. These are the 5 switching angles. So that will be giving you individual harmonic less than 3% and the total harmonics less than 5%. This is computed and you can go for switching at these angles. First quadrant switching angles. So this is the plot of THD versus modulation. As you know, the modulation index, whenever it is in MD, whenever it is increased, so modulation index, if it is increased, obviously the THD will be less. So how it is decreasing, you will see. For 5 switching angle, it is decreasing. So this is for your unipolar PWM. So equations is a bit different here. So in the same case, the equation is set to 0, then the fundamental is your equated to M, but the equation is a different one or unipolar. So the angle pattern switching for unipolar is also different. Now, before coming to this, I must explain this. In the earlier case, whenever you are eliminating the selected harmonics, you are eliminating only those harmonics which you have selected, not addressing the other harmonics. But in the PSO technique or the soft technique, what you are doing, you have set this problem as an objective function, right? What is that objective function? It is the THD, percentage THD. This is objective function. So within that, you have this selected harmonics along with that other harmonics, right? So in the first case, conventional SHA technique, you are eliminating the targeted harmonics, but you are not addressing the other harmonics. But here, we are targeting those selected harmonics to restrict up to 3%, but we are mainly interested to minimize the objective function, that is the THD, percentage THD, and there the other order of harmonics are still there which is not targeted. So what is done in the minimization technique? They are taking care of the other harmonics. So which is not targeted, still that is being addressed, and finally the percentage THD is being minimized. So that is the reason, though the selected harmonics are not completely eliminated, still the THD is less compared to the earlier one. So that is the beauty of this soft technique, and you are complying with the target set by IEEE 519, and at the same time you are having lesser THD, right? So that is the reason. So initially there might be a confusion, but this is not a confusion. Now, whether this technique is better or not, only you can say whenever you are comparing with a standard practice or standard methodology, right? Now, there are 2 persons who are pioneer in this field. One is your Tolbert, the other one is your Chiasson. One is your electrical engineer, the other person is Chiasson is a mathematician. So these 2 persons have several published work in this field of SHE, and they have introduced several mathematical theory and technique for solving those nonlinear equations. So they were only concerned with those nonlinear equations, how to solve it effectively. At the beginning I told you this is the nonlinear equations. Analytically it is very difficult to solve. So these 2 persons, one is a very famous person in mathematics, Chiasson, is a Russian person. Second one is the electrical engineer fellow. So these 2 fellows have worked in several ways to solve those nonlinear equations. And one famous technique they have found is the resultant theory. where it can be solved very effectively, and they have taken care of some non-linearities to certain extent, not exactly it was resolved. So that resultant theory, using that resultant theory, the same model, the angle was computed, and then finally the THD was computed. Now that is compared here. So one, you can see here, this is your proposed PSO technique, this line, and the dotted line is your using that resultant theory which was formulated by Chiasson and Tolbert. Very big personalities in this field and pioneer in this field to one. So that was compared here. Now obviously in the dotted line here you can see at this place there is a non-linearity. At this place there was a non-linearity where the solution is not available. On the other hand, if you see the percentage THD in every places, here you can see from here to up to 1.1 or more than 1.1, the percentage THD is always lower than this resultant theory which is used to compute the THD. Always only at a place higher than 1.2 it was found that resultant theory was giving better THD, I mean lesser THD than this PSO technique. It is more than 1.2 MD, that is modulation index. But up to this is always lower. The reason is that they are eliminating the selected harmonics only. They are not addressing the other order of harmonics. That is the reason. So percentage is always less. So it is better result it is giving, and you are complying with IEEE 519, no problem. Now this is one method of assessing in the bipolar. So the same thing has been used in unipolar also. So it is tested. Now this is the spectrum. So what I mentioned here, that is shown in the spectrum itself. So voltage harmonic spectrum, it is shown for bipolar switching, 5 switching. So in the 5 switching you are not completely eliminating, so that is why it is not 0. So you see 5th, this is not 0, 7th it is not 0. So sorry, this is probably your 3 switching angles per quarter. 3 switching angle per quarter. So for 3 switching angle you can eliminate 2 harmonics, not more than that. So you are eliminating only this one, 5th and 7th. You cannot eliminate others. And the 11th is again coming because you are restricting to 3%, this one and this one. 11th is coming. And you see, interestingly, the angles are selected in the random search method in such a manner the other harmonics are optimized. And interestingly, this 13th is almost 0, it is less than 3%. We are not targeting 13th. 13th is not targeted at all. Only the constant was 5th and 7th. It was set to less than 3%. So that is fulfilled. But as I told you, the percentage THD is considered as a objective function which is to be minimized, and along with that you are considering up to 30th order of harmonics. So the rest of the harmonics are optimized, and that's why the 13th is eliminated and these are also minimized, so that percentage THD is less. So this is the reason. Similarly here, this is for MD 0.8 modulation index, this is for 5 switching angle. So for 5 switching angle, one is set for your fundamental and the rest 4 can be eliminated. You have 5 variables, so you can solve 5 equations. One is for fundamental and the remaining 4 harmonics can be eliminated. So this is your 5th eliminated, 7th, 11th, 13th. These 4 are eliminated, not eliminated, limited to 3% or less. So this is the spectrum, both experimental and simulated results are shown. Okay. Now, why we are doing all these things? Naturally the question comes, why we are doing all these things? Because our intention is to give a better quality power to the microgrid or to the grid. Moreover, there is a stringent measure. If you are violating those IEEE standard, penalty will be imposed upon you as a electricity generation company. So you must comply with those terms and conditions. So for that you have to do all these things. Now one practical aspect I am telling you related to this. If you go to purchase UPS as an electrical engineer, you never ask what is the quality of the output power. You never ask. You just check the value, I mean cost of the product. It is 1500 rupees, 0.5 kVA, and this is 2000 rupees, 0.5 kVA, same rating. So let us purchase this 1500 rupees UPS. But the problem is that they have no other facility to give you better quality power. Whenever there is a power cut, you are using this UPS to run your device, maybe your computer or any other sophisticated device. But at that time, your device is subjected to that polluted power because no such filter or intelligent switching is adopted in the converter circuits. So that's why it is very cheaper one. But if you go for a good quality UPS, then you check the power quality, you will find it is a very good one. Harmonics percentage is very less and the distortion is very less. So that is not going to affect your sophisticated gadget or devices. So that is more important. So whenever power was not available, people were not concerned about this. They wanted only power. We are having load shedding, so we need power. So people are crying for power. Now power is available. Now they are asking for quality power. Not only power, quality power. Same thing for drinking water. Whenever drinking water was not available, people were asking for drinking water. Once it is available, they ask for quality drinking water, not polluted one. So same thing is here. Anyway, this is something else. This is for unipolar switching. Earlier one was bipolar. This is for unipolar switching. This is different pattern of switching. So in unipolar switching, this is also tested. This is for 5 switching. Earlier one was for 5. So in unipolar, the number of harmonics are less. The THD will be also less. Now this is the experimental validation. Output voltage waveform. The 5 bipolar switching is shown. This is for unipolar switching. The output waveform is shown. Now, once you propose something, it has to be tested in different platform. You cannot say this is better one. I have tested it for unipolar switching. I have tested it for bipolar switching, 3 switching per quarter cycle, 5 switching per. It is a better one. I have tested it with this famous resultant theory, which was devised by Chiasson and Tolbert. So it is a better one. You cannot say. Still, there are several things. Your system has to be tested with that platform or on that platform. So, multi-level inverter, that is very crucial because whenever the voltage level requirement is higher, you have to go for multi-level inverter. So, in that multi-level inverter, if you adopt the same switching pattern, whether still it is giving you better result or not, that has to be tested. So, it is tested here in multi-level inverter. So are you getting more? So it should be interactive one. This should not be one-way traffic. I am just going on discussing, you are just listening, not that. Whenever you have any confusion, anything, you may ask anything. You are free to ask anything you can ask. I will try my best to clear it. So in the beginning I told you, it is very difficult to teach a teacher because teachers are supposed to know many things. And from those participants, I will be also in a very good position to learn something. So that is the beauty of discussing such thing in the FTP or sub program. Now, in the multi-level inverter, this is the configuration, common configuration I have shown you, cascaded multi-level inverter. In this configuration, the devices are used in a bridge configuration, and finally the output is taken. So obviously, in each leg, the voltage which is available, that are being added, and finally the voltage which is available in this terminal will be added, and it is a higher level voltage. So that is used for a higher level voltage applications. Now this is the waveform how it is done. For a 11 level multi-level inverter, it is done. Say alpha 1 to alpha 5 or 5 switching per quarter cycle. So this 11 level means if you go on more and more level, as you can see here, the steps will be more, and as a result the harmonics will be less. This is a common practice. If you go for higher level, 11 level, if you go for 13 level or even higher level, then the steps will be more, and as a result it will be more similar to your desired sine wave, and the harmonics will be less, right? So 11 level is shown here. So again there is a restriction. You cannot increase the level because there is a practical problem of implementing it experimentally. So 5 VDC is considered, plus minus 5 VDC. Now this is for multi-level. Again the equation is different. So that equation is derived here. So for fundamental, again the same application. Here the M is for fundamental value. The other selected harmonics can be equated to 0 in case of your conventional SHE technique. Right. Now in the same manner, switching angles versus modulation index is computed. This is for PSO technique. We are not equating to 0, we are restricting to 3% or less than 3% for individual harmonic, and Ph.D. less than 5%. So this is for 7 level inverter, alpha 1, alpha 2, alpha 3. 3 switching angles are considered. These are the pattern of angle to give you the desired result. This is for 5 switching angles. The pattern is computed. Now one thing I must say here, you might be thinking this is a very good method, why people are not considering earlier? It is not like that. It has many limitations. I am telling you, whenever you are running that algorithm, I am showing you, it may not be giving you the best result. You have taken care to find the best solution, that is the G best or the global best, but it may not be giving this one. What happens whenever you are running this, every time it tries to minimize the objective function and it finds some absurd result. What are those absurd results? Sometimes it exceeds the constant. Say it is limiting some other harmonics which you have not targeted, and the harmonics which have been targeted might be increasing more than 3%. So it is not that in a single run you can have the best result. So what you will have to do, you will have to introduce some sub loop. Within that loop, putting some other constant so that it may not exceed those constants. And after running several times, you will find the result. And that best result you will have to observe and you will have to store in the DSP. Only then you can implement it. So basically this is not an online technique. This is not an online technique. You will have to compute it by running this algorithm, and you will have to find the value for each and every modulation index. Say 0.5 to 1.2 or say 0.4 to 1.3, like that. So for every modulation index with a difference of 0.01, you have to compute the angle. And then in between these two, if there is any non-linearity, then it will be optimized. And at that angle it will be fired and it will give you the best result. So which is not possible in the conventional technique. There is a non-linearity, no solution is available, you cannot find any angle. But here, the algorithm is developed in such a manner, it will find the optimum value between these 2 points, say between 0.61 to 0.62. If there is a discontinuity, at that instant, it will optimize the angle and it will find the angle taking the average of 0.61 to 0.62. And that will be a very good one. It is found. Experimentally also it has been tested. It is a very effective value. But analytically you cannot find the solution. That's why discontinuity is coming. So this modulation index, whatever index versus the switching angle you are computing, that is not found in a single run of this algorithm. I am telling you, let it be clear. So you will have to run several times, and that is the limitation of your random search technique. Though initial guess is not required, but still you have to run several times, so you don't know whether this is the best one or not. There might have some other best solution still remaining there. So you will have to run several times, and then ultimately you have to find the best value, which is giving the minimum THD value. Then you store it in the DSP. In this way, it is a offline computation. Then finally, it is stored in the DSP, and then it is run at any time. That is done using that DSP, which is stored in the memory, and then it is used. Now here, interestingly, again it is compared with the best technique. Here, this same technique, nobody has proposed this thing. This is just experimentally, out of experiment it was found. Some additional switching is used within the fundamental switching. What are those things? Let us go to the next slide first, otherwise it will not be clear. This one. So here you can see, in every step you can find from here to here you need the switching, na? From here to here you need the switching. So within this switching there are some spikes like this one. What are those things? These are actually additional switching. So in between this fundamental switching, some additional switchings are used. Number of switching will be more. Say in your 5 switching angle, you have introduced some extra switching, say 2 switching. So total number of switching will be 7 here. Now with the conventional 7 switching per quarter cycle, what you are doing? You are eliminating more number of harmonics, but THD minimization will be more here if you use 2 extra switching along with 5 fundamental switching instead of going 7 fundamental switching. So that is tried here. In between the fundamental switching, some additional switching is introduced, and due to that the THD is minimized compared to yes. So this is the fundamental switching, this one is for fundamental switching, and with additional switching, 2 additional switching we have used. Due to that this THD is more reduced here. Now let us consider the additional switching as a number of switching. This is for initial one, this one for 7 level, this is for 11 level. Now the same 2 persons, they are the pioneer. I am telling you, these 2 persons, Chiasen and Tolbert, these 2 persons are the pioneer in finding these different approaches in SHE technique and solution of these nonlinear equations. So they have developed another very famous theory, that is called the active harmonic elimination theory. So I can share you those reference paper also if you are interested. The active harmonic elimination theory, that is another famous one, similar to our earlier one. Which was the earlier one? The theory which yes, no, the theory. Resultant theory. So this is your active harmonic elimination. That is another remarkable achievement by these 2 persons. Active harmonic elimination they have developed, and the same technique is used here with the same number of switch. To compute the number of switching for the same system. So here in active harmonic elimination, if you consider the same THD, they have reduced this THD 5% or less. For the same reduction by this proposed PSO, what are the number of angle required? So here I have compared with the number of angle with that famous active harmonic elimination technique, considering the same THD 5% or less. So here the number of angle you see for 0.6 modulation index, here proposed technique, this one is the number of angle, total number of angle in a cycle. So this one fixed. From here it is reduced, but in active harmonic elimination you see the number of angle, it is from here, from 0.6, it is very high compared to this one. Number of angle is very high for a complete cycle. Only up to this, here it is same. Beyond 0.8, I mean 0.85 modulation index, the number of angle in both the method is same. But in the lower modulation index, particularly below 0.85, the number of angle, switching angle for reduction of THD to 5% is very high compared to this proposed technique. So that is another aspect which is compared, because the number of switching angle, if you go on increasing the number of switching angle, the automatically THD will be reduced. That is not a very good job. But you cannot go on increasing the switching angles. That is a lot of problems. Switching losses are there and your complex circuit will be coming up. Then percentage THD is compared for 5 switching angle. Now we have considered it for the 5 number of switching angle for both the technique, resultant theory and this PSO technique. This is not active harmonic elimination, this is your resultant theory, an earlier one which we have considered. Here again the percentage THD is considered for multi-level inverter. So this is for resultant theory developed by Chiasson and Tolbert, and this is for PSO technique. So here it is always percentage THD is here higher, this is almost similar, then again higher, at this point higher, only at this point it is a bit lower, again higher, then here it is lower, it is higher, then at this point it is lower, resultant theory is lower, and here also lower. So at certain points, particularly at higher modulation index, it is lower, but at the lower modulation index it is very good one, but here again it is very high, from 0.8 to 0.9 it is very high. So in this way, overall if you consider, then it is giving a better result. So this is for multi-level inverter. So it has been tested for unipolar switching, bipolar switching and multi-level inverter. So this is the spectrum which is shown. So here you can see absolutely zero in 11 level inverter, not zero, it is very less, close to zero. I am telling you this is not zero, but graphically it is scale is chosen in such a way that it is showing almost zero, not exactly zero, very less. So in multi-level inverter, as you can see, the THD will be less for same number of switching compared to the unipolar or bipolar. So this is for 11 level inverter. Now this is the additional switching which I have shown. This is the waveform, almost sinusoidal, almost for induction motor load, current waveform. So this is harmonic spectrum. Now here you can see it is coming at this level, here at more than 0.9 kilohertz it is coming, this one. Now the final stage is considered in a microgrid. So before connecting to microgrid, several other platforms have been used to check the versatility of the system. Now we are coming to microgrid. So here again an experimental strategy has been used to reduce it, not using the directly that method only. So what is done here, we have used two sort of switching in combination. So a microgrid here is considered, say considering this one here, a fuel cell stack 1 and stack 2, then this is connected with a IG, that is induction generator, it is connected. As you know, induction generator output is dependent highly on the velocity of wind, right? So that is a variable parameter. So this is uncertainty is there. So what is done? It is connected with a rectifier, constant rectifier, to convert it to DC. Then DC link inverter is used here. From DC to AC again it is converted, so that you can have the voltage at a desired frequency. So irrespective of your changes here in the output due to wind speed variation, the magnitude may be varying but frequency will be remaining here same. You are not allowing the change of frequency but magnitude may be different here. So that is taken care of by this inverter, DC link inverter. Now this is your control pulses which we are generating by this DSP TMS320F2407. So that is stored here, already stored, offline computed then stored here in this DSP for switching this multi-level inverter. Now this one, these two are not exactly that one. One is your normal PSO normal sine triangle technique is used. So this is microgrid configuration. Now what we are doing here, this is a combination of PSO based technique and sine PWM technique. So experimentally we have used two converters. One is having the switching pattern from this PSO, proposed PSO based technique, and the other one is the normal sine SPWM method. Sine PWM, sine triangle we have used. What is that technique? Here, depending upon the frequency of the reference wave, up to a certain level the harmonics will be completely eliminated and the first bandwidth will be available. First harmonics will be available with sideband at MF plus minus 2. That value will be depending upon the reference frequency. So that technique is used, reference sine wave, then triangular sine wave, and the selected lower order harmonics like 5th, 7th, 11th, 13th are eliminated by PSO technique using 5 switching angles per quarter cycle. So PSO technique is used for eliminating these 4 selected order of harmonics, right? And the frequency and phase of the triangular carrier wave is chosen such that the first dominant harmonics with sidebands is opposite to the first prominent harmonics order present in the system after elimination of selected harmonics. So that is the interesting thing, how it is done. If you change here this phase angle alpha, phi, this one, in the triangular carrier wave, if you change this phase angle phi, then the amplitude will be changed. If you change this reference frequency, this one, frequency of the triangular carrier wave, here if you change the frequency, this one, then also the value of the first dominant harmonics or the sideband will be changed. That depends upon the when this first harmonics will be coming, that is dependent upon this carrier wave frequency, this one, and the amplitude of the phi will determine the direction of the harmonics, whether it is in the positive direction or negative direction. So by changing this phi you can change. Now it is chosen in such a way, so first you have eliminated 5th, 7th, 11th and 13th, right? Then the first harmonics, which is a prominent one, will be appearing after a certain value. You target that value. So up to that, all other earlier harmonics will be eliminated. If you choose this omega in such a manner, this carrier wave frequency, that all other harmonics prior to that will be eliminated, and that first dominant harmonics, the polarity will be chosen by this phi in such a manner that it is opposite to the earlier one, which is eliminated. So you have eliminated, say you have 3 multi-level inverter. So first inverter and second inverter is exactly turned on with this technique, PSO PWM technique, and these 4 harmonics are eliminated. So the next dominant harmonics will be appearing in the system at a certain point. Then the third inverter which you have used, you go for switching of that inverter with the conventional SPWM, and then here you choose this omega and this phi in such a manner that up to that value all other previous harmonics are eliminated. So it is not injecting something else. Only first dominant harmonics will be there, and that is opposite to the one which is already present after elimination of 5th, 7th, 11th and 13th. So that technique is very effective one. Though it is a in the experimental stage. Still now it is very difficult to apply, because you cannot choose this harmonics every time so that it will be opposite to the dominant one. It is very difficult. But in certain cases you can find it. So that was tested. So in that way, it is selected, is almost similar to the earlier one, the 5 switching angles, eliminating the 4 harmonics. Then 19th harmonics appears. 5th, 7th, 11th, 13th, these are eliminated. So 19th is appearing after elimination of those. Then 19th is plotted here. How 19th harmonics can be changed with the change of phi and the frequency of the second option, that is the sine PWM. So that is a bit complicated one. So that is plotted here. You see in the 3D picture, the carrier wave phase wave angle, that is phi, with the change of angle phi, how it is varying, and the modulation index, how it is changing. So phi is, magnitude is dependent upon this frequency, you cannot change it, only you can change the direction. So that is plotted here with the modulation index, how the 19th harmonics is changing in the conventional sine PWM inverter. So from here you can choose the appropriate angle where it will be exactly opposite to the existing one. I mean 19th harmonics should be counterbalanced by this sine PWM 19th harmonics. So that angle has to be chosen. So this is not a very easy job, I am telling you. So every time you cannot find it, you will have to store it, and then you can go for selecting that angle according to your requirement. So that is shown here. So this 5th, 7th, 11th, 13th is eliminated. 1, 2, 3, 4 is eliminated. 7th is optimized, is not eliminated. And this 19th is targeted. So 19th, you see in the PSO PWM, 19th is chosen in such a way that it is in a negative direction. Sorry, PSO PWM, it is coming in the negative direction, and that's why the SP sine PWM is chosen so that it is in the positive direction. So it will be countered this 19th, and as a result THD will be decreased. So this is the combination of these two switching, and we can try this thing for other combination also. This is a bit complicated. So this is the comparison is made. This is first one is for only using PSO. If you go for PSO, the proposed technique of switching in all the multi-level inverter in the microgrid, then THD will be this one, with the changes of modulation index. But if you go for combination of sine PWM and the proposed PSO, then it is further reduced to this value with the changes of modulation index. So that is a comparison that is made here. But still I am telling you, this is in the experimental stage, this is very difficult. If someone is interested, they can work on it. It is very interesting area. So this is the experimental setup which is used here. IGBT, these are used. The 2.2 kilowatt induction generator, this is used for the microgrid. This is for sine PWM, the carrier phase angle and MD and 19th harmonic. This is also stored in the TMS320F DSP, and this is how it is implemented. FFT analysis is done. Now these are the line current of the two, I1 and I2. This is for with PSO and SPWM combined approach, and the I2 is for only PSO. So here you see I2 line current with only PSO based inverter. So basically lot of these harmonics are here, but in this combination to a great extent it is reduced. Still there are, because you cannot eliminate completely, I am telling you, there is no such a technique till now which is available to eliminate these harmonics completely. It is impossible. You will have to eliminate up to 100. So this is your line current, voltage waveform. This is the voltage spectra. Now this is the conclusion. That means how it is effective. So the proposed technique, this is already discussed as a multi-level inverter. In the both method it is utilized. Other SHG technique can result in discontinuity. Unlike other iterative technique, the proposed method does not depend on initial guess. That is very important one. How will you select the initial value while randomizing? There is no such technique. You can select any value, ultimately you will have to converge at the particular point. Is successfully applied to multi-level inverter with lesser number of switching angle, and it is combination of sine triangle and also the PSO technique. This in combination it is also used. These are some of the references related to this work. Thank you. So any queries from your side, you are free to.
Sir,
Yes.
sir, which harmonics have the most significant effect on the audience and why?
No, harmonics actually, if it is very close to fundamental one, that is going to distort your fundamental more. Which one is more? That means close to the fundamental means say 3 times of your fundamental. Third is not considered, it is eliminated. Then 5th, 7th, 11th, these are very close to fundamental. Huh? So that's why we are targeting lower order harmonics. Lower order harmonics means which are close to fundamental. Higher order harmonics, even if it is having greater magnitude, that is not going to distort very effectively. So lower order harmonics are always targeted. And as per IEEE, you have to consider at least up to 30. At least up to 30th order you have to consider. But theoretically up to 100th harmonics, that is also affecting your fundamental. Because what is your harmonics? It is a, if you go for analyzing a composite wire, it will give you one fundamental and the other will be say 3 times of your fundamental, then 5 times of your fundamental. This is combination of all this, then you will have the composite wire. Okay? Any queries from any side? Okay, thank you all.
Thank you very much, sir, for accepting our invitation and sparing a valuable your time. And it's a very useful and thought-provoking lecture. I think participants will be benefited out of it. Now I request my co-coordinator, Dr. Vikram Das, to present a small memoir to sir. Please.
So I am actually
Sir.
also host. So I am a permanent faculty member. So I am not a guest. So
Temporary guest. Thank you, sir. Now this is time for lunch. We can understand. So food court, Rajesh and others, they are going. So everybody can move to the food court. Yeah. Sir, lunch. We will